Alright everyone, we're back. We're going to start with question 9 now. Students use a catapult to investigate projectile motion. In their first experiment, a ball of mass 0.1 kilograms is fired from the catapult at an angle of 30 degrees to the horizontal. Ignore air resistance. In this first experiment, the ball leaves the catapult at ground level with a speed of 20 meters per second. However, instead of reaching the ground, the ball strikes a wall 26 meters from the launching point, as shown in figure 8a. Figure 8b shows an enlarged view of the catapult. Right, question is calculate the height of the ball above the ground when it strikes the wall. Show your working. Alright. So, with a question like this, typically what you need to do is work out how long it would take for the ball to travel that distance horizontally. And then using that time, you would then say, okay, well, what's the height of the ball after that time? Okay, so it's kind of a two-part thing. Alright, so how are we going to work out the first part? How long does it take to get from there to there horizontally, just considering horizontal motion? Okay, well, with projectile motion questions, if there's no air resistance, then we assume that the horizontal speed is the same throughout the motion of the ball. In this case, the horizontal speed is going to be given by 20 times cos of 30 degrees. Okay, that provides the horizontal component of that initial velocity. So that ball is going to be traveling horizontally with this speed throughout the entire thing. Okay, yes, it's also got a vertical component to its motion, but we're just looking at the horizontal component for now. Okay, so how do we work out how long it takes to travel a distance traveling at a certain speed? Well, that's your speed equals distance over time triangle. Okay, so we want time, so that's distance divided by speed. So time equals distance over speed. In this case, the distance it travels is 26 meters horizontally, divided by the speed, 20 cos 30. Alright, and if we do that, we end up with 1.5, according to my calculator. Let's just double check. 26 divided by 20 cos 30. Just make sure your calculator's in degrees mode. There you go, 1.5. Alright, so that's how long it takes for the ball to go from there to there. Alright, now the second question is, well, what is the height of the ball at 1.5 seconds? Okay, and for this we need to use vertical components of motion. So we want to know how high is the ball after a certain time. So what is the what is the vertical displacement of the ball? And what do we know about the ball's vertical motion? Well, we know its initial vertical velocity, uy. Well, that is this component of the initial velocity, which is 20 sine 30. Alright, so that's 20 sine 30. We know how long it takes for the ball to get to where it's going, and the vertical acceleration is gravity, negative 9.8. Just make a note, it has to be negative because we've assumed up is the positive direction here. Right, so there's your S, U, T, and A. So the suitable equation for this is S equals UT plus half AT squared. Sub everything in, so U is 20 sine 30 times time, 1.5, plus half times negative 9.8 times 1.5 squared. Alright, let's do that. So 20 times sine 30 times 1.5 plus half, or 0.5, times negative 9.8 times 1.5 squared. 3.975. So it is 3.975 meters above the ground when it hits the wall. Alright, let's double check the examiner's report. So it's question 9a. Yep, there we go. So they round it to 2 sig figs, so 4.0 meters. Students demonstrated a range of inappropriate techniques, suggesting they did not have a clear strategy for solving these types of projectile problems. Students should be mindful of how they set out their working so they can clearly demonstrate their understanding of how to solve multi-step problems such as this. Not very helpful in terms of their report. I mean, almost half got 0, and then almost the other half got full marks. So you either know what you're doing or you don't. The intermediate marks probably came from, 1 mark for calculating the time taken and then not knowing what to do from there, something like that. I guess the idea is make sure you're familiar with projectile motion questions, right? Typically, you're going to have to do things in 2 parts. One of those parts will involve using purely a horizontal motion, in which case you assume that the horizontal velocity is constant throughout the motion. And then once you have that, usually you work out a time based on that, and then from that, using that time, you then work out something to do with the vertical component of motion. Or it could even be the other way around. Okay, you could work vertically first, work out a time, and then use a horizontal component to work out like how far it travels, what's the range of the projectile. But usually they're those 2-part kind of questions, so 2 steps. All right. Part B, students next investigate the relationship between various initial variables and range R on the level ground. So the range is just how far it travels from where it started. As shown in figure 9, in this experiment, so in this second experiment, they use a 0.1 kilogram ball and keep the catapult at a fixed angle of 30 degrees during the experiment. The ball lands at the same height as it is fired. Okay, so that's your setup there, and they're just, I guess, varying some things. The variables in this experiment can be classified as controlled, dependent, or independent. Complete the table below by providing 1 variable from the experiment for each classification. Okay, well, we just use some variables here, I guess, to fill in the blanks. So which one would be our controlled variable? So this one would be the one that you don't change. In this case, it looks like they're using a fixed angle of 30 degrees. So you could write angle. Dependent variable, well, let's work out the independent variable first. So the independent variable is the one we are changing ourselves. So we're investigating the relationship between various initial variables. It doesn't actually say. I mean, I guess we can assume that we're changing the speed. I mean, there's a hint here in part C. So I'm going to say we're changing the speed. So initial speed U. Whoops, I put in the wrong box. I'm talking about initial. So initial speed U. And by varying the initial speed, we are then seeing how far it goes. So the range would be the dependent variable in this case. There you go. All right, I guess another controlled variable we could say is the mass of the ball. But the question does ask, provide 1 variable from the experiment for each classification. So I wouldn't put 2 of them, just in case they get angry at that. So I guess mass of ball would be another one you could put here instead of angle. Okay. Just check the examiner's report for that one. Most students knew what they were doing. 57% got full marks. And there you go, controlled mass of the ball or the launch angle. Dependent would be range, and independent would be launch velocity. That's what we've got. All good. So, next one is students gathered data from a series of experiments similar to the one described in part B. Here's your data. So, it looks like we're changing the initial speed, and then we're seeing how far it travels, and we're just recording that down. The students use a tape measure that is marked with intervals of 10 centimeters to measure the range that the ball travels at different initial speeds. On the grid provided below, graph the data gathered by the students. Include scales and axes on each unit. Include scales and units on each axis. Insert appropriate uncertainty bars for the range on the graph, and draw a smooth curve of best fit. Okay, now it's going to be hard for me because I can't really draw with a ruler on here, but I'll do my best. So first things first, this is 8 marks just for graphing this stuff. So there's a lot that you can get taken off in terms of your marks here. So just be as very careful as possible. I'm going to do everything first. I'm going to pause it and then write everything, and then I'll explain what I've done, just because it will take a lot of time to actually put everything in there nicely. So I'll pause it, and then all of a sudden magically there'll be a bunch of stuff here. Alright, we're back. So there's magically appeared stuff on the screen. Let's explain what has happened here and see where the marks come from. So on the grid provided below, graph the data gathered by the students. So that's simply me just filling in the data points where they should go. And to help me do that, I've got a scale on the bottom and a scale on the side. Okay. Now you want to try and make your data fit, like maximize the graph. Don't draw it all in one tiny little corner. All right. Look at the range of your data here, and try and spread these values out as much as you can on the grid that's provided. Okay. So I've gone for 2 tick marks for every one along my horizontal axis, and I've treated every tick mark on the vertical axis as 0.1, and that sort of fills it in nicely and makes you able to draw it much more easily. Alright, so probably a couple marks for that. Include scales and units on each axis, so that's just your numbers and also units. So they haven't provided us with units, so I've got to fill that in myself. Initial speed was meters per second and the range was in meters. That comes from the table here. Alright, insert appropriate uncertainty bars for the range on the graph. So the range is the vertical value. Now it tells us here that they've used a tape measure marked with intervals of 10 centimeters, which means that means our uncertainty is going to be half of that, which is 5 centimeters. Now if I've said that one tick mark is 0.1 meters, that's 10 centimeters, then half a tick mark is 5 centimeters. So your uncertainty or error bars have to have a length of 5 centimeters or half a grid line. Okay, and you just fill that in as best you can for each of the dot points that you've got, and draw a smooth curve of best fit. So it's not going to be linear. Okay, it can't be linear because if you try and draw a line of best fit, it won't go through all of your error bars. So it has to curve, and that's why they've specified a curve of best fit rather than a line of best fit. So you just try and draw your curve nice and smooth that sort of goes through all of those error bars. Okay, and if your graph looks something like this, nice and neat, all right, everything's scaled and labeled appropriately, full marks for that. Okay, let's quickly read the examiner's report. So yeah, you either got no marks, and you sort of were able to get marks up to 5. Most people got between 5 and 8 marks. Common errors included omitting the units on the axes, incorrect or omitted uncertainty bars, and ruling a straight line through the points. Okay, I've addressed all those things. There were also some students who placed the initial speed on the y-axis and the range on the x-axis, despite the axes already being labeled. So just make sure you've got the right things in the right spot. This suggests that students need to spend more time identifying independent and dependent variables. Okay, well, there's not too much that I can say here that I haven't already said. Just be very careful when you're graphing data like this. Okay, try and draw it nice and neat, and make sure that you can try to make sure that it's going to be as easy as possible for the examiner to read what you've done. Okay, and just make sure you've included everything that needs to be included there. All right, and that's it for that question. So question 10. Let's do it. So the length of a spaceship is measured to be exactly 1/3 of its rest length. All right, 1/3 of its rest length as it passes by an observing station. What is the speed of this spaceship as determined by the observing station expressed as a multiple of c? All right. So this sounds like it's going to be a special relativity question, specifically to do with length contraction. So it says the length of a spaceship is measured to be exactly 1/3 of its rest length. So we can set this up. L equals 1/3 of L0. Okay. As it passes by an observing station, what is the speed of the spaceship as determined by the observing station? Right. So the true relationship between contracted length and rest length is L. Sorry, wrong way around. I'm thinking of time. Is L0 over Lorentz factor. In this case, it appears that our Lorentz factor, just comparing the equations, is going to be 3. So gamma equals 3. Now we know gamma is equal to 1 over the square root of 1 minus v over c squared. We know that's equal to 3. And the rest is now just algebra trying to solve for v over c, because it wants it as a multiple of c. So once I have the value of v over c, I just write that number in the box here. Okay. So the algebra, well, I mean, I can swap out the square root and the 3. So I get, I'll do it down here. So 1 over 3 is equal to the square root of 1 minus v on c squared. Square both sides, I get 1/9 equals 1 minus v over c squared. Swap the v over c squared and the 1/9, and I get v over c squared equals 8/9. That's 1 minus a 9th. And then the square root of both sides, v over c equals square root of 8 over 9, which is 2 root 2 over 3, I think. And it doesn't say to put it in exact form or anything like that, so we can work out what that is, and we'll end up getting 2, I'll just do square root of 8 over 9, around 0.94, so it's 0.94 c, around 94% the speed of light. Let me double check that I've done it right. Yeah, there you go. Okay, cool. So you either didn't know what you're doing or you did know what you're doing. That seems to be the case for most questions. Alright, let's keep going. Question 11. Tests of relativistic time dilation have been made by observing the decay of short-lived particles. A muon travelling from the edge of the atmosphere to the surface of Earth is an example of such a particle. To model this in the laboratory, another elementary particle with a shorter half-life is produced in a particle accelerator. It's travelling at blah 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 times c, which we're saying is gamma equal to 20. Scientists observe that this particle travels 9.14 times 10 to the negative 15 meters in a straight line from the point where it was made to the point where it decays into other particles. It is not accelerating. A. Calculate the lifetime of the particle in the scientist's frame of reference. Okay, so we want to know how long the particle exists for, I guess. Okay, so it says it travels this length from the point where it was made to the point where it decays. So from the scientist's point of view, we could work out how long that particle lives for. This is just a speed equals distance over time formula, because we've got how fast it's going, we've got how far it travels, we want to know how long it lives for. Okay, how long it takes for that to happen. So this is just t equals distance over speed. Distance it travels is 9.14 times 10 to the minus 5 divided by the speed it travels, which is that fraction of the speed of light. So that times 3 times 10 to the 8. And this should give us how long it lives for in the scientist reference frame. Okay, so 9.14 times 10 to the negative 5 over 0.99875 times 3 times 10 to the 8. There you go. So 3 point, oh, I missed it. 3 point, we'll go 3 significant figures. 3.05 times 10 to the, and I missed that again, times 10 to the negative 13 seconds. All right. All right, let's double check. Yep, there you go. Okay, so either again, you didn't know what you're doing, or you did. The most common error was to calculate the correct time and then apply a time dilation to the result. Okay, so again, scientists observe that the particle travels this length, calculate the lifetime or how long it takes for that to happen in the scientist frame of reference. So we're not mixing reference frames here, so you don't need to do any time dilation or length contraction formula. This is purely just speed equals distance over time. Part B, however, calculate the distance that the particle travels in the laboratory as measured in the particle's frame of reference. Okay, now this is where we start thinking about time dilation. So the particle, now we've got to think about this carefully and make sure we're setting up the variables properly. The particle measures, if we're talking about distance, the particle will always measure the longer distance. Okay, in your own frame of reference, if you're traveling from one point to another, the distance that you calculate you're traveling, that's always going to be a contracted length. Okay, so imagine you're saying, okay, points A and B. Let me try and draw a picture to visualize this. There's points A and B. Okay, and you're someone here like watching something move from that point to that point. Okay, but the points themselves aren't moving. All right, so you're standing here, you're the scientist watching this thing happen. All right, but the points themselves aren't moving. So if you imagine putting a stick from there to there, that stick's not moving. But if you're the muon, okay, this stick is now moving back that way, and you're the one that's stationary. Okay, and because the stick is moving, the stick will appear to be contracted according to the muon. All right, so this distance will appear to be contracted according to the muon. So contracted length is what the muon's length measurement would be, and that is the original length divided by the Lorentz factor. We're told the original length is, or the rest length I should say, is 9.14 times 10 to the negative 5, and divided by the Lorentz factor, which is 20, and so that's going to give us 9.14 times 10 to the negative 5 over 20. 4.57 times 10 to the negative 6. Alright, there we go. Let's double check. Yep, 4.6 times 10 to the negative 6. Okay, again, the most common error was to correctly identify the form of the equation, but they confused proper length with contracted length. So even when I'm doing these questions, I really have to sit down and think which one is going to be contracted, which one is going to be the proper, or if you're talking about time dilation, which one's dilated time, which one's proper time. I have to sit there and think. It doesn't come naturally to me, unfortunately. Some people, they can just visualize it straight away. I have to always go back and think, okay, what's the definitions of contracted length and what's the definitions of dilated time? I always have to try and visualize this picture that I've drawn. It just doesn't come naturally to me. So really try and make sure that you understand which one is which and that you're putting them in the right spots into the formula. Okay. All right. Part C, explain why the scientists would observe more particles at the end of the laboratory measuring range than classical physics would expect. Okay. Well, have a think. In terms of the length that... Actually, we can't... should I use length in this question? I might use time dilation to answer this question. Okay, so in terms of the time, the lifetime of the particle, okay, how could I put this nicely? So, alright, I think I'll explain it like this. So, according to the muon, they don't have to travel as far, okay? So it takes a shorter amount of time for them to travel that distance, which means for the muons, from the muon's perspective, they're going to be able to travel that distance of this laboratory and still be alive. Okay, I'm talking like anthropomorphically here, but you know, they haven't decayed yet because they reached the end in a shorter time than their normal half-life. Okay, so we would expect more particles to be detected simply because from the muon's reference frame, they don't have to travel as far to be detected, and therefore more of them would reach that detection point before they decay. Okay, so that's one way to interpret the answer to this question. Okay, purely based on the time it takes the length of their journey, um, in terms of how far they can travel before they can decay. All right. The other explanation would be in terms of time dilation. So from the muon's reference frame, it hasn't actually been calculated here. But if we were to calculate the lifetime of the muon, we're basically going to use this distance and the speed here to work out the time it takes for the muon to decay in the muon's reference frame. And it will be shorter than this question, this answer up here. So according to the scientists observe more muons reaching the end where they can be detected, because in the scientist frame of reference, they live longer. All right, the time of their lifetime has been dilated, it's been extended. So simply more of them can reach the end before decaying. So there's two explanations that could be provided here. Only write one of them down. Okay, so I'm not going to write anything. I'll just go straight to the examiner's report. So students were required to confirm that it was time dilation that was responsible for the scientist's results. Due to the particle's velocity, its half-life as measured in the scientist's frame of reference is increased. Therefore, fewer particles will decay before reaching the detector and more particles will be detected. So that was the second explanation I provided. It was possible for students to explain the scientist's results by applying length contraction. In that case, they needed to identify that due to the particle's velocity, the distance to the detector as measured in the particle's frame of reference is reduced. So this was the first explanation I provided. Now, the fact that the majority of students got nothing means they just didn't know how to respond to this kind of question. Okay, now keep in mind this was the first question of its kind for the entire study design, of this version of the study design. So probably they weren't expecting a question to be worded like this, or whoever was teaching at that time didn't expect a question to be worded like that. So it may just be that as a factor, but yeah, I mean, you've seen this question many times in class, and similar questions will be asked in subsequent exams, and these two responses are quite stock standard for this kind of question. So just make sure you understand what's going on in these two responses here. Okay, I'm not going to write anything down. Refer to examiner's report. All right, question 12. Students are using two trolleys, trolley A of mass 4 kilos, trolley B of mass 2 kilos, to investigate kinetic energy and momentum in collisions. Before the collision, trolley A is moving to the right at 5 meters per second. Trolley B is also moving to the right at 2 meters per second, as shown in the figure. The trolleys collide and lock together, as shown in figure 10b. Determine, using calculations, whether the collision is elastic or inelastic. Show your working and justify your answer. Okay, I can tell you now that whenever two things stick together after the collision, it is always inelastic. Okay, it is not possible to be an elastic collision if the two things stick together afterwards. Right, but we still have to prove it. So let's see how that works. So elastic and inelastic is a kinetic energy thing. Okay, so using kinetic energy to answer this question. All right, so how do we show something is elastic or inelastic? So you just compare the total kinetic energy before the collision with the total kinetic energy after the collision. Okay. The problem with this, though, is we don't know how fast the two things are moving after they collide. Okay, and then stick together. So to answer that question, I need to first use conservation of momentum to work out what is the final speed after they collide. Okay, so let's do that first. I'll do two columns just because there's two steps to this. So using conservation of momentum. So m1 u1 plus m2 u2 is equal to the combined masses times its combined velocity there. All right, so we're working out this v. Let's do that. So it's going to be m1 u1, so 4 times 5. We're going to say to the right is the positive direction, and b is 2 kilograms traveling at 2 meters per second, and that's going to be equal to 4 plus 2, which is 6, times v. All right, 4 times 5 is 20, plus 4 equals 6, so 24 divided by 6 is 4 meters per second. Okay, so that's how fast the two trolleys A and B are traveling after they stick together, right? Now, kinetic energy to show whether it's elastic or inelastic. So energy before, that is an atrocious spelling of the word before. So that's just half mv squared for block A or trolley A, which is half times 4 times 5 squared, plus the kinetic energy of trolley B, so half times 2 times 2 squared, and you can just chuck that on a calculator. I'll just do it in my head real quick. So 2 times 25 is 50, plus 4, so 54, I think. Yeah, 54 joules. I'll double check that in a second. I'm just going to rush through this. You might have done it already and got a different answer. That's okay. I'll correct myself if I'm wrong. Now, the kinetic energy after. Okay, well, you treat this as one thing now. So there's a combined mass of 4 plus 2, which is 6. And we've worked out it's traveling at 4 meters per second, so 4 squared. And that's going to be 3 times 16, 6, 12, 18, 1, 2, 3. So that's 48 joules. So it's lost kinetic energy in total. And then you say 54 not equal to 48, therefore inelastic. Okay, that should be enough to show the examiner you know what you're doing. All right, don't want to waffle on about, oh, it's inelastic. You don't have to write a whole sentence about it. Just say, yep, I know the kinetic energy before, know the kinetic energy after. I know they're not the same, therefore it's inelastic. Okay, let me just double check my numbers are right. So report. Yep, okay, so work it out the final speed. That was all this stuff on the left. Then we worked out the initial kinetic energy, final kinetic energy. They're different, therefore the collision is inelastic. Okay, this is a pretty typical kind of question. So just make sure you understand how you do all that. Question 13. Pat and Robin hang a mass of 2 kilograms on the end of a spring with a spring constant of 20 newtons per meter. They hold the mass at the unstretched length of the spring and release it, allowing it to fall as shown in figure 11. So that's the unstretched length of the spring. You hold a mass there, and then you just move your hand, and the mass obviously is going to fall. Okay. Determine how far the spring stretches until the mass comes momentarily to rest at the bottom. Show your working. Okay, so this is what's happening. Okay, there's the spring with the mass. You let the mass go. The mass is going to go down, slow down, slow down, slow down, stop. Right, it's going to stop there, and then it's going to come back up. Right, and it's going to like oscillate between these two positions. Now, in the real world, it would lose energy every time it bounces up and down and eventually come to rest somewhere in between. But we don't care about that. We just want to know when we let it go, what's the lowest position that it reaches. Okay. Now, how are we going to do this? So this kind of question is typically a conservation of energy question. So when it's held at the top here, it has all gravitational potential energy. It's not moving. The spring is not stretched. So there's no kinetic energy. There's no spring potential energy. It's purely gravitational potential energy. Right? When it falls, yes, it's moving, but then when it reaches the bottom, it's not moving anymore. Okay. Now at that point, we can call that zero. Okay, ground level, whatever. So there's no gravitational potential energy there. That is now all spring potential energy. Okay. So during this interaction where it's traveled from this position down to the bottom, it loses gravitational potential energy, but it gains the same amount of spring potential energy. Okay? So that's how we're going to answer this question. How much gravitational potential energy does it lose? So we're going to say, what is the change in gravitational potential energy? Well, that is mass times g times delta h. Cool. I don't know what delta h is. So, well, that's what we're trying to work out, aren't we? How far does the spring stretch? So to help me answer that, I'm now going to equate this to how much spring potential energy it gains. Okay? So it gains half times k times delta x squared spring potential energy. Okay, and in fact I can rub this part out now because that's all I need. All right. Now our job is to work out delta h. Okay, how far? Well, or delta x. Okay, because they're both the same thing, aren't they? How far you fall is the same as how much the spring stretches. Okay, so those two quantities are the same. And we can actually use that to our advantage here because I can now cancel one of those quantities from each side. So that cancels out with one of those delta x's. Okay, and so now I have, if I now solve for delta x equals 2mg, because half multiplied by 2 across there, over k. And this delta x will tell me how far the spring stretches. And that is equal to 2 times the mass, which was up here, 2 kilograms, times g, which is 9.8, over the spring constant, which is 20. All right, so what's that going to be? 2 times 9.8 divided by 20. 1.96. There you go. So apparently it's 1.96 meters. Okay, so this was a very typical conservation of energy question. What energies are present at the top? What energies are present at the bottom? Those two values have to be equal, and then you can set that equation up and then solve for your required quantity. Check the examiner's report. Okay, yep, they basically did exactly the same thing. So they just, instead of using delta H, they just used X, but essentially they've done the same thing. Okay. It says a common error was to use mg equals kx. This is when you only use this when you sort of gently lower the mass so that it reaches like a final stationary point and then doesn't move after that anymore. Okay, so that's the only time when you would use this formula. So this is equating the gravitational force with the spring force, and making them equal means that one is pulling the other one in the opposite direction, but they're equal in magnitude. So the net force is essentially 0, which means that your object's not accelerating. Okay, and most of the time that's applied in the context of lowering the mass so that it just, when you let it go, it doesn't move anymore. Right? It's just its natural rest position. Okay, part B, explain how the three energies involved and the total energy of the mass vary as the mass falls from top to bottom. Calculations are not required. Okay, so explain how the three energies involved and the total energy of the mass vary. Okay, well, we can say the total energy remains constant because that's just what happens in an isolated system. Total energy remains constant, but the individual energies vary. Okay, so what happens to the gravitational potential energy? Well, it decreases because you're going from a higher position to a lower one. Okay, so you can say gravitational potential energy decreases. The spring potential energy, well, you're now stretching the spring, so it's storing that spring energy in it, so it starts to increase. And what happens to the kinetic energy? Well, initially it's at rest, so the kinetic energy is at 0. Then when you let it go, it begins to fall, starts accelerating up to some point, but then eventually it starts to slow down again. So you can say that the kinetic energy initially increases, but then decreases to 0 when the mass reaches the bottom. Okay. Calculation is not required, simply just a description of what's going on here. So let's quickly head over to the examiner's report, double check what they wrote. Okay, the gravitational potential energy is maximal at the top and decreases. Spring potential energy is minimal at the top and increases. The kinetic energy is 0 at the top and increases to its maximum in the middle before decreasing to 0 at the bottom. The total energy of the mass Oh, okay. All right, my mistake. So they're treating the spring as a separate thing. That makes sense. No, that makes sense. So it's total energy of the mass, or the total energy of the mass. Oh, that's a bit of a funny worded question. The three energies involved and the total energy of the mass. Yeah, okay. All right, fine. Whatever. All right, so they've said the total energy of the mass decreases because the mass itself doesn't have any spring potential energy. It's the spring mass system that has spring potential energy. So, if you're just talking about the mass, then yes, I guess uh, there is no spring potential energy, and because you have less gravitational potential energy at the bottom than you did at the top, and the kinetic energy is zero at the top and the bottom, then yeah, sure, the total energy decreases. Because kinetic energy plus GPE decreases. Okay, sure. Not happy with that wording, but we'll accept that. That's fine. All right, I'm going to just quickly pause, get a drink of water. You should go take a break too. It's been 41 minutes, and we'll come back in a second. All right, I'm back. So let's keep going. Question 14. A light ray from a laser passes from a glucose solution with refractive index 1.44 into the air, refractive index 1, as shown in figure 12. Cool, so there's a laser here in glucose, and it's pointing up to this point here. Calculate the critical angle for total internal reflection from the glucose solution to the air. Okay, critical angle comes straight from your notes. Just trying to see which page it's on. What? Where's Snell's law? Why don't I have Snell's law on here? Do I have the wrong formula sheet? Okay, that's oh no, there it is. Okay. Alright, n1 sine theta 1 equals n2 sine theta 2. Okay, so that's Snell's law, but we want critical angle for total internal reflection. So we want the refracted angle, I guess you can say, to be 90 degrees. Okay, so that's going to be 90, this theta 2, and our job is to solve for theta 1. Okay, so let me just quickly write that down. So n1 sine theta 1 equals n2 sine of 90 degrees, because we want total internal reflection to occur, which means we want this refracted ray that comes out here to have an angle of refraction of 90 degrees or more, right? Well, the critical angle is when it reaches 90 degrees, and then total internal reflection will happen after that. So we want to solve for theta 1. So sine of 90 degrees is actually just 1. For those of you who do methods, you'll already know that, but put sine of 90 degrees on a calculator, it just turns into 1. So theta 1 would be the inverse sine of n2 over n1. That is inverse sine in this case. N2 is where we're going, so that's air, so 1. And N1 is 1.44. That's where we're coming from. And chuck that on a calculator. So inverse sine 1 over 1.44. 43.98 or 44 degrees. Okay, so any angle of incidence greater than 44 degrees, so if this angle here is greater than 44 degrees, total internal reflection will occur. Okay. Part B, the light ray strikes the surface at an angle of incidence to the normal of less than the critical angle calculated in Part A. On figure 12, sketch the ray or rays that should be observed. So we're striking the angle of we're striking the boundary here at an angle less than 44. So some refraction will occur, something will exit here and go out that way. but also there'll be a little bit of this light reflected back in at the same angle that it hit at, okay? That always happens when you're going from one medium to another. So one of the rays would be like this, so that would be the refracted ray, but then there'll also be another one that's going to be like a bit fainter than the original, that would go down like that, okay? I'm not sure if that's exactly what the question wants. I mean, it's 2 marks, so I'm guessing there's 2 rays, but let's just double check the report. Yep, they wanted 2 rays, like that, okay? And the answer from before was also 44 degrees. Cool. All right, let's keep going. Part C, the angle to the normal is increased to a value greater than the critical angle. An observer at point X in figure 13 says she cannot see the laser. Explain why the observer says she cannot see the laser. Well, it says here the angle here is increased to a value greater than the critical angle. Okay, so obviously if it's greater than the critical angle, total internal reflection is occurring. So that's all you have to say. Total internal reflection occurs at angles greater than the critical angle. Oh, what's going on with my spelling? Okay. Therefore, no light will exit the glucose for the observer to see. Okay, I don't know how else I could put that. Let's double check the report. Yes, the phenomenon is a total internal reflection. The light ray is reflected back off the interface into the glucose solution, which is why the observer cannot see it. Yeah, it makes sense, okay? Alright, keep going. 15. How much more do we have left? Just check. 15, 16, 17, 18, 19. Alright, I'm going to just do this in one big go. So we're going to go over an hour, I think. I'm at 47.5 minutes. Alright, let's go. So question 15. Physics teacher intends to demonstrate the phenomena to her students. Demonstrate wave phenomena to her students. She takes her students to the school oval to listen to a 680 Hz sound. The speed of sound in air is 340 meters per second. Calculate the wavelength of this sound. 1 mark, very easy. It's a wave equation. V equals frequency times wavelength. So we want the wavelength equals speed of sound divided by frequency. Speed of sound is said to be 340 there, and the frequency is said to be 680. So 340 over 680 is 0.5 meters. Easy. 1 mark in 30 seconds. Alright, the teacher now sets up 2 loudspeakers placed 4 meters apart with the sounds in phase. That just means if one's emitting sound at a peak, the other one's also emitting sound at a peak, and they're both emitting the same frequency of sound. 7 students are placed in a row 24 meters from the loudspeakers as shown in figure 14. Each student is 1.5 meters away from the next student. Student 4 is in the middle and is exactly the same distance from each loudspeaker. When a single loudspeaker is sounding, all the students hear very close to the same intensity. Okay, so that's our setup. The teacher now connects both loudspeakers. One student, Ellie, predicts that now they will hear a similar sound of double the intensity. Another student, Sam, disagrees. He says the intensity of the sound will depend on each student's relative distance from each speaker. Part B is now evaluate Ellie's and Sam's responses. Okay, so Ellie says they will that I'm assuming all of them will hear a sound of double the intensity. Sam says no, it will depend on where they're standing and their relative distance from each speaker. So this we have to interpret as a wave interference question. We've got 2 sources of coherent waves, and you know what happens when we have 2 sources of coherent waves. The waves spread out, and at certain points they will interfere with each other in such a way to produce regions of constructive and destructive interference. That's your classical interference pattern, okay? So along the lines that we know are nodal lines of interference, there will be very little to no sound, but some of them will have antinodal lines where there is quite a loud sound if you are standing on one of those antinodal lines. So Sam seems to be the one that is correct. The sound will depend on each student's relative distance from each speaker. Ellie is wrong because if you are happening to stand on a nodal line, then you will hear a quieter sound than someone who may be standing on an antinodal line. Okay, so that's the evaluation of their responses. I'm not going to write it down again. I'll just say refer to examiner's report. And let's have a quick read. Okay, Sam is correct, Ellie is wrong, and why? Addition of a second speaker will produce an interference pattern. Yep, we mentioned that. The intensity that a student hears will depend on the path difference between the two speakers. Yep, we mentioned that in the roundabout way because the path difference determines whether you're on a nodal line or an antinodal line. Alright, cool, I hope that makes sense. Move on. Part C, will students 2 and 5 in figure 14 hear similar or different sound intensities? If you predict that one of these students will hear a higher sound intensity, state which student and justify your prediction. Show your working. Okay, now, the first time I think I ever saw this question, it didn't click to me that there was an easy way to do it. And what I actually did was I said, okay, let's use a whole bunch of trigonometry to work out how far this student is from speaker 1, how far away they are from speaker 2, look at the path difference, figure out what the path difference is saying. Is it going to be a node or an antinode? Then they do the same thing for student 5. How far are they from speaker 2? How far are they from speaker 1? What is the path difference? Is it a node or an antinode? But then I realized you don't have to do that. Okay, we have a formula that tells us the distance between, say, this. So we know that this is going to be an antinode. We've got a formula that tells us the distance from this antinode to the next one, and from this antinode to the next one, and from this. I'm not saying the kids are antinodes, but from this antinode to the next one, and we know the one right in the middle is going to be an antinode. Okay. Sorry. So that formula is delta x equals wavelength times distance to in terms of this equation, it will be the distance from the speakers to this line of kids, and that's all over d, which is going to be the distance between the speakers themselves. Okay, so this delta x is going to tell us the distance between successive nodes or between successive antinodes. And we've got all of this information to be able to work that out. So the wavelength coming from the speakers is up here, what we determined in part A, so 0.5. The distance from the speakers to the line of kids is 24 meters. And the distance between the speakers themselves is 4 meters. Okay. So I'm not even going to use a calculator for this. 24 over 4 is 6, and then actually I'll just do 12 over 4, so that's 3. So 3 meters. Okay, so again, what is this telling us? It's telling us that if this is an antinode, which we know it is because they're equidistant from the speaker, you're on the central antinode line, then 3 meters either side of this person will be the next antinode. So that means that's 1.5, that's 3. So this kid's standing on another antinode, and this kid's standing on another antinode. And the kids halfway between antinodes must be standing on nodes. Okay? And if the question is, compare what student 2 hears and compare what student 5 hears, well, student 2 hears loud sound, student 5 hears soft sound. Okay? So we can say student 2 here's a louder sound than 5. We can say, according to the above calculation, that 2 is on an antinodal line, and 5 is on a nodal line. Okay. All right. Cool. So that was a much easier way to do it than I did it the first time I saw it. Let's check the report. There you go. So, yep, they've done the same thing. So they've worked out the distance between antinodes. And they've said, yep, student 2 is 3 meters from the center, so they'll hear an antinode. Student 5 is 1.5 meters from the center, so they'll be at a node. Yeah. It does say a number of students found the path differences using Pythagorean triangles and determined the correct answers that way. That's what I did, but it took about 10 minutes. Yeah, it was a long way to do that. Sorry, I'm just going to pause, get another drink of water. My voice is starting to go. I've been talking for 3 hours now. Alright, let's keep going. Question 16. Standing waves are formed on a string of length 4 meters that is fixed at both ends. The speed of the waves is 240 meters per second. Okay, I'm going to highlight fixed at both ends. That's important. Calculate the wavelength of the lowest frequency resonance. Okay, so lowest frequency. Let's talk about standing waves, fixed at both ends. Simplest standing wave is like this. Okay, this is the fundamental frequency, which is the lowest. The next possible standing wave is, now there's a node in the middle as well. Okay, this is called the second harmonic frequency. All right, and you can just add another node progressively, all right, and fitting them in equally spaced in between the two fixed ones. So if the question is calculate the wavelength of the lowest frequency resonance, let's calculate the wavelength of this frequency. Okay. Now, if the string is fixed at both ends, then we have the following formula for frequency. Actually, I'll just say Fn is Nv over 2L. So F1 would be 1 times V. So V here is 240. That's the speed of the wave on the string, over 2 times the length of the string, 2 times 4. That is, I don't know why I'm doing this, 240 over 8, it's going to be 30. So 30 hertz. And therefore, the wavelength of that lowest frequency is speed of the wave divided by its frequency. So 240 divided by 30, which is just 8. Meters. There you go. And that, we could have just got that from the picture here, okay? One wavelength is just a continuation of that. If that from there to there is the length of the string, so 4 meters, then another 4 meters again will give you the wavelength of that standing wave, so it'll be 8 meters. But at least we've proved it with calculations. Calculate the frequency of the second lowest frequency resonance. So that's F2. Okay, F2 is 2 times the speed. So that's again using this formula here. Over 2 times the length. Whoa. And that's just going to be double this one, which is 16. Sorry, no, what am I doing? Not double that, double this one. Okay, so it's going to be 60. Double check. 2's cancel out. 240 divided by 4 is 60. So it's all good. Okay. So your fundamental frequency is the lowest frequency possible. And then every harmonic frequency above that is just a multiple. Okay, so the next multiple along. Alright, but again, here at least we've proved it with calculations. Part C. Explain the physics of how standing waves are formed on the string. Include a diagram of your response. Okay, so it really varies between person to person about how you're going to answer this question. Include a diagram in your response. Okay, the only thing I can really think of is you've got, so okay, let me just explain in words and then I'll just tell you to refer to the examiner's report. So what happens in standing waves is you've got, there's the string, all right, and you send a wave down starting at this end. Okay, so you send a wave, I'll draw it in red. You send a wave down, okay, and this looks like the wave. Oh, whoa, what happened there? It deleted itself. Okay, let's do it again. All right. Why is it doing that? It won't let me draw. Come on. Are you going to let me draw? Now I won't. Okay, it's going nuts. How about I just show you the exam report? Okay, so what I was going to say is that when you send a wave down the string, the wave, when it reaches the other side, it reflects back onto itself, okay? When the reflected wave then interferes with the original wave that you sent down, that's when the standing wave occurs, okay? There's some nice animations that you can find online. Just type in standing wave animation or standing wave GIF or something, and there's plenty of them on there for you to see. But all you have to do is say waves traveling in opposite directions are reflected at the ends. So one fixed end there, another fixed end there, or on this diagram it's here and here. The waves overlap and they interfere to produce an interference pattern, and then I guess draw some kind of diagram explaining that. But it's actually really hard to draw a static diagram of how standing waves are formed. This isn't really a diagram of how it's formed, it's just showing you one variation of the standing wave. Okay, this is the second harmonic, which isn't really descriptive. It just says like that's what it looks like. Okay, but I don't really like how that question is. Include a diagram in your response. If the question was like draw a diagram of the second harmonic standing wave, then yeah, that would be fine. Okay, but to actually draw a static diagram of how standing waves are formed is quite complicated. Okay, but this explanation hopefully makes sense. All right, let's keep going. Question 17. In an experiment, blue light of frequency blah 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 is shone onto the sodium cathode of a photocell. The apparatus is shown in figure 15. So as soon as you see something that looks roughly like this, immediately you should think photoelectric effect. Okay. The graph of photoelectric current versus potential difference across the photocell is shown in figure 16. So this is a current versus voltage graph. Okay, very standard graph for photoelectric effect questions. The threshold frequency for sodium is 5.5 times 10 to the 14 hertz. What is the cutoff potential when blue light of frequency 6.25 times 10 to the 14 hertz, so that's the same as the one that's shining on it currently, is shone onto the sodium cathode of the photocell, referred to in figures 15 and 16. Okay, so cutoff potential, also known as stopping voltage. It's asking us to calculate what that stopping voltage is. Now, it says that the threshold frequency for sodium is that. Okay, that is our F0. Okay, below this frequency, nothing will be ejected because the photons don't have enough energy to do anything. Now, how do we relate threshold frequency and stopping voltage? Well, there's a nice formula that we use, and that's based on this one here. Okay, it is simply going to be this one. Okay, or maybe even this one. So our threshold frequency is going to be F0. The stopping voltages you can replace with E here. Okay, if we're talking about electron volts. So the stopping voltage V equals H times F0. Okay, so V0 stopping voltage is equal to H times F0. We just have to make sure that we're using EV version, the electron volts version. Okay, whenever you're mixing voltages and frequencies and stuff, you have to use electron volts, and the hint is in the name of the unit. Electron volts means we're dealing with voltage. Okay, so stopping voltage is just 4.14 times 10 to the negative 15. That's your Planck's constant H times the threshold frequency 5.5 times 10 to the 14. And you calculate that, it'll just jump straight over to your guide, and that is, I've completely misread the question. Okay, never mind. I was mixing stopping voltage and work function, wasn't I? Alright, let's start again. So, that's the threshold frequency, but blue light is being shone. Okay, so because a frequency higher than the threshold frequency being shone on the sodium metal, electrons will be ejected and they will have some extra kinetic energy. The kinetic energy that they have extra, if we write that in terms of electron volts, that will also be equal to the stopping voltage. Okay, so what is that extra kinetic energy that they're getting? That comes from here. Okay, kinetic energy is the HF. Now this F here is the actual frequency being shone on the metal, minus the work function, which is what I was mistakenly trying to work out before because I misread the question. That is F0. Okay, H times F0. And you can factor out that H and you get F minus F0. So now that becomes 4.14 times 10 to the negative 15 times, okay, what's the actual frequency shining? 6.25 times 10 to the 14 minus the threshold frequency 5.5 times 10 to the 14, and that equals, and now that makes a bit more sense, that equals 0.31 volts. Okay, yes, I know I'm using a formula that's got energy, but remember, if we're calculating the energy of these photoelectrons in terms of electron volts, that value is equal to the stopping voltage required to stop those electrons from crossing the gap. Okay, so those two numbers, the numerical value of those things, are equal. So it's 0.31. Okay, my apologies for the mix-up there. Part B, on the graph of photoelectric current versus potential difference shown in figure 16, sketch the curve expected if the light is changed to ultraviolet light with a higher intensity than the original blue light. Okay, so our job is to draw what happens to this graph when we change to this light with this higher intensity. Okay, now I think that two things are going to happen here. Okay, ultraviolet light has a higher frequency than blue light, therefore a higher energy. Okay, what's going to happen is, because it's got higher energy, it's going to take more stopping voltage to stop the electrons that are being ejected. So I claim that the stopping voltage is going to shift from here to here somewhere. Okay, if we're going to be consistent, we'll draw it on the graph. So it's going to start somewhere there maybe. Okay, then because it's being shone at a higher intensity, that means there's more photons hitting the cathode, and so more photons means more electrons ejected, which means higher current. So your graph's going to look something like this. Okay, the higher current goes up there, and you've also got a higher stopping voltage. That's what I predict. Let's see if that's the case. That's what they're expecting. Yes, they're expecting that. There you go. Okay, so I hope my explanation made sense for that one. C. The results of photoelectric effect experiments in general provide strong evidence for the particle-like nature of light. Outline two aspects of these results that provide the strong evidence that is not explained by the wave model of light, and explain why. Again, I'm going to refer you to the examiner's report because we're running out of time and my voice is starting to go. Okay. Now, there are three things that happen in the photoelectric effect that can't be explained by the wave model. Those three things are here. Negligible time delay, the existence of a threshold frequency, and the independence of stopping voltage from intensity. Okay? the wave model predicts that there should be a time delay, okay? Because the energy of the wave needs to build up on the surface of the metal to then finally be able to eject the electrons. So we should be able to shine light onto the cathode, and then eventually, once enough light has been shone for enough time, then there should be enough energy built up on that cathode to then eject the electrons, okay? But we don't see that because there's negligible time delay, okay? So the wave model can't explain that. The second one, the existence of a threshold frequency, that sort of ties into the first one, in that if you leave the light shining, if we're assuming a wave model, if you leave the light shining on the cathode, okay, if you leave the light shining onto this thing for enough time, eventually, doesn't matter what kind of light you have, eventually the light will have built up enough energy on here to eject the electron, okay? But the fact that we see a threshold frequency means that it doesn't matter how long you leave that light shining on that cathode, nothing's ever going to happen, okay? So the wave model fails to explain why that happens. The last one here, the independence of stopping voltage from intensity. So assuming we're talking about the wave model, then that means if we're talking about intensity of a wave, in the wave model, the intensity refers to how much energy is in that wave, okay? Sort of like the amplitude of that wave. And so if you have a more intense light wave, then you should expect the stopping voltage to increase because you've got more energy in the electrons that you're ejecting. But we actually don't see that. Increasing the intensity of the light doesn't change the stopping voltage. It simply changes the current, and the wave model can't explain that. Okay. The report also says that many students spent a great deal of the response discussing either the results of the photoelectric effect that did not refer to the wave model, or discussing the particle explanation for the phenomena described above rather than the wave predictions. So the question is, outline two aspects of these results that provide the strong evidence that is not explained by the wave model. Okay, it doesn't say anything about the particle model here. Okay, yes, it says up here it provides evidence for the particle model of light, but that's not what they want you to do. They want you to say two of these things, okay, and why can the wave model not explain that? All right, those are where your marks come from. Now, I wasn't marking this one, so I don't know exactly what they were looking for. Don't know how these marks were allocated, but you've got to make sure you refer to the actual question. Okay, so don't assume it's asking for you to do something. Read it and then address that and nothing else. Okay, last two pages. So, an energy level diagram for sodium is shown in figure 17. Part of the emission spectrum of sodium vapor includes a photon of energy 1.65 electron volts. Alright, so what's going to happen is there's going to be a emission spectrum. So anywhere that's white means there's no light there. And one of your parts of the emission spectrum means there's a line. And that line corresponds to 1.65 electron volts of energy. Okay, well, that's what the frequency or the wavelength of that particular light has in terms of its energy. Assume that C equals 3 times 10 to the 8. Here's your energy level diagram, okay, for sodium. Part A, draw an arrow on the energy level diagram to demonstrate the atomic energy level transition resulting in the emission of a 1.65 electron volt photon. So all we've got to do is draw an arrow between any two lines where the difference between those lines is 1.65 electron volts. Okay, and I can only see one pair of lines which has a difference of 1.65, which is the n equals 5 state and the n equals 2 state. Okay, so 3.75 minus 2.1 is 1.65. Is it an absorption or an emission? Is the arrow pointing up or down? This is an emission, which means the electron is losing energy and that energy gets emitted as a photon. So the arrow has to point down. What is the shortest possible wavelength of a photon that can be emitted when the atom decays from the n equals 5 level to the ground state? So the shortest possible wavelength means also the largest possible frequency, okay, because they're inversely proportional to one another. So what is the largest possible frequency? Well, that corresponds to the largest possible energy, which means it's from the n equals 5 straight down to the bottom, isn't it? Okay, that's the largest possible energy jump that could happen. So the largest possible energy jump is just from 3.75 down to 0. So it's 3.75 electron volts. Now we're going to convert that to a wavelength. So the formula is E equals hc on lambda. And so lambda equals hc on E. Because we're dealing with electron volts, h is the electron volts version. So 4.14 times 10 to the negative 15 times the speed of light divided by that energy change, which was 3.75 electron volts. And I'm going to jump straight to the answer here. 331 nanometers. So your calculator will probably spit out 3.31 times 10 to the negative 7. But because your unit is in nanometers, okay, it's got to be in nanometers, okay. I'll just quickly do it on the calculator so you can see what it would spit out for you. 4.14 times 10 to the negative 15 times 3 times 10 to the 8 over 3.75. There you go. So that's what it's going to give you. But if you press engineering, it'll swap it to negative 9, and that's your nanometers there. Whoa, hang on. I forgot a 4. That's why my answer is different. Thought I clicked 4. There you go. 331 times 10 to the negative 9. So 331 nanometers. All right. A student reported observing a spectral line corresponding to 2.5 electron volts. In terms of the quantized states of the atom, explain why this would be impossible. All right, well, can you see a spectral line of 2.5? That would only happen if there was an energy jump between any two energy levels that corresponded to having a difference of 2.5 electron volts. Now, none of these energy levels, any pair of them, none of them have a difference of 2.5. Okay, you can go through and check all of them. Every pair of energy levels, none of them has a difference of 2.5. Okay, so you can just say there is no transition between the energy states of the atom that has an energy level change of 2.5. Okay, the the examiner's report simply, too far. It says exactly what I just said. There's no transition with energy difference of 2.5, therefore no such emission is possible and no photon of this energy can be observed. Okay, now that's not to say we're looking for an energy level at 2.5 electron volts. We're looking for a difference in energy levels of 2.5 electron volts. Okay, right, so I'm just going to say refer to exam report. Okay, last question. We've now gone 1 hour and 18 minutes. Roger and Mary are discussing diffraction. Mary says electrons produce a diffraction pattern. Roger says this is impossible as diffraction is a wave phenomenon and electrons are particles. Diffraction can only be observed with waves, as with electromagnetic waves such as light and X-rays. Evaluate Mary's and Roger's statements in light of the current understanding of light and matter. Describe 2 experiments to show the difference between Mary and Roger's views. Okay, again, refer to study, refer to exam report. Okay, we'll talk about it quickly and then we're done. So, well, Mary is right. We know this now because we've seen in our notes that electrons do produce diffraction patterns that depends on their momentums and their de Broglie wavelengths. Okay, Roger is wrong because it's not impossible. So Roger's wrong, Mary is right. Why are they right? And can we describe 2 experiments that show that? So we've talked about in the notes that electrons can be passed through like crystal, like thin crystals, and the spacings between atoms in crystals are very regular, so that's why it works really well with crystals. It's like passing an object through a gap, like a wave through a gap. Right, that gap is very consistent, and so that will always produce that nice diffraction. Electron slit experiments. Okay, so electron single slit experiment or double slit experiment. We've discussed those in the notes. Those are two experiments that produce those diffraction patterns. Okay, especially in terms of like Heisenberg's uncertainty principle, we've seen that the electrons diffract as they pass through the opening. That's why they spread out. Okay, and the Heisenberg's uncertainty principle is just one interpretation of why that's happening. Okay, but it can also be explained in terms of the fact that it's a wave, and waves just diffract when they go through an opening, right? So there you go. All right, those are three options there to talk about. You only need to describe two of them, and just whether or not Mary is right or wrong, and whether Roger is right or wrong. Just have a read of that. I mean, you can pause it and read it yourself. I think, yeah, this map one here, Mary is correct for electrons and Roger is correct for light. I mean, the statement is Roger says this is impossible. Yeah, so Roger is wrong. Roger's not half right, he is wrong. He says it's impossible, but it is possible. So you can't sort of say someone's half right. You have to evaluate their response, and they're either right or wrong. Okay. Don't try and copy things from your cheat sheet. See how crazy I'm going after 3 hours? You just read the question, read what each person is saying, talk about what you know based on the theory. Okay, so we know electrons produce a diffraction pattern. We know Mary's right. Roger is wrong because he says it's impossible. And describe two experiments that show the difference between Mary and Roger's views. Well, we're just showing why Mary's right, I guess. So it's either of those three experiments. Okay, there you go. And the rest is just formula sheet. Cool, so I hope that's helpful. I'm going to do another exam soon, 2018 most likely, and we'll see how far we can get with those. Alright, let me know if there's any glaring errors that I've overlooked in the comments, or just email me and I'll, I don't know, write what's wrong in the description, I guess. Alright, good luck.